Hello everyone and welcome to another video. Today I'd like to talk about interacting with a Simulink model from a Matlab script. So in essence, we'll talk about how to set up Simulink model parameters and execute the Simulink model from a Matlab script. In addition, we'll look at how to import and export data between Matlab and Simulink so the two can be used synergistically. In terms of a more formal agenda, let's first start by talking about how to define Simulink model parameters within the Matlab workspace. Related to this is we'll take a gander at how to run a Simulink model from a Matlab script. Once all that's running, we'll take a look at how to send simulation data back to the Matlab workspace using a variety of methods such as a out1 block, a To Workspace block, as well as logging the signal. Finally, we'll look at how to use Matlab data as input to a Simulink model. We'll do this using just one method, namely using the from workspace block. Before we jump into Simulink, I'd like to revisit the model we built in our previous video entitled Ordinary Differential Equations and Dynamic Systems in Simulink, and use this as a motivating example. Needless to say, if you haven't had a chance to watch this yet, please go through this tutorial first before continuing further. You can get to this video via the link in the description or via the link that has just shown up on your screen. Now, if you recall, the system we considered earlier was a simple pendulum with some viscous friction at the pivot, as well as an input torque at this same location. The linearized differential equation governing the system was shown to be this. Now, in the past video, we assumed these constants, which led to a simplified version of the differential equation. We then built a Simulink model to numerically solve/simulate the simplified differential equation. Now, while we were able to get some good results using this model, this approach should have raised some red flags, especially to those of you with a software development background. Namely, we hard-coded these constants into the model. So if we want to go back and change parameters of the model, like the length or mass of the pendulum, it would involve hunting through the Simulink model and replacing all the appropriate values in the various blocks scattered throughout the model. So if you think about it, the generalized version of the differential equation that I'm circling up here in blue is vastly superior. So why don't we try to implement this version of the equation in Simulink where we use variables to represent the constants rather than the version with the constants already hard-coded into the blocks. Alright, so we've got Matlab up and running, and in the interest of time, I've gone ahead and just recreated the model that we built in the previous tutorial. So this is the one that we were discussing here, but we notice here that the constants are hard-coded into here. Let's just double check to make sure that this runs here. So I'll go ahead and hit run, and look, that ran. And here's our first hint of where this might be able to help us. Namely, if we go back to Matlab, you notice I just ran the Simulink model here, and notice that it actually created a variable in my Matlab workspace. So it seems evident that Simulink is talking to Matlab. Maybe it goes the same way. Maybe it goes Matlab can talk to Simulink. So to do that, why don't I come back here to this pendulum model, and let's try to go ahead and implement the improved version or the generalized version of the differential equation. So if you remember, I think this gain right here, instead of being 1/5, this should have been c over the quantity m times l squared. And let's hit OK, and maybe let's make this gain a little bit bigger so we can actually see that value. Great. And similarly, this gain, instead of being 10, it was actually g over l here, right? And then finally, I think one more thing. I think there was supposed to be a gain up here, which actually ended up being just a 1 with those constants. That's why we don't have a block here. But in this case, we do need a gain. So I'm just going to go ahead and insert a gain here of the appropriate value. So the appropriate value that should go in here, I believe, is, let's go ahead and open this block up. This should be 1 over the quantity m times l squared. All right. So there we are. Again, let's open this up a little bit so we can see that it's in there. And we see right now, Simulink has variables to represent all of these constants here. So let's go ahead and save this model here. And if we hit run, as you can probably imagine, we get a whole bunch of errors here because it has no idea right now what c, g, m, l, any of these constants are here in my model. So obviously it's not going to work. Now, the way we're going to solve this here, or the interesting behavior that we should observe here, is that when you hit run on a Simulink model, what it's going to do here is it's going to come back and look for those variables, any variables in the model here in the Matlab workspace. So since it didn't find it here through that error, so in order to fix that, all we need to do here is let's come over to Matlab and start ourselves a new script. And in this script, let's go ahead and define all of those constants that we need in our Simulink model. All right, so let's come here to my script here, and I'll maybe say this is a script to illustrate how to interact with a Simulink model from a Matlab script. Let's make this a little bit bigger just so that to get the line break correct. Okay, so again, let's go ahead and start with our usual clear CLC close all. And what we saw right now is what I would like to first do with this script here is define model constants. So what I mean by that is we should define in here all of the constants that are needed in that model. So I think gravity, we were using a value of 10, mass, we were using a value of 1, C was a value of 0.2, and the length of this was, I think, a value of 1. So let's go ahead and save this file here, and what we should do here is we should save this in the same location as our Simulink model, just out of good practice. And I'll go ahead and maybe call this, let's just call this Matlab Script to interact with Simulink model. I know that's a bit of a long verbose name, but this is really what we're trying to do. We're trying to make a Matlab script that's going to interact with that Simulink model. So if I go ahead and save that, again, let's just double check. Yep, here it is. I've saved the script in the same location as the actual model that I'd like to interact with here. The reason I like to do that is so that when I go ahead and hit run and I change my folder to that directory, it's going to be in the same directory as the model here. So if I go ahead and change the folder, we see now that what Matlab has done with our script here is it's defined those variables in the workspace. So now if we come back to our Simulink model, maybe let's just resize this a little bit so we can see everything together. Earlier we saw that there was an error when we tried to execute it, but now when we do this, what we're going to do is we're going to hit play. Simulink is going to realize that there are a lot of variables here in this model. It's going to look in the workspace, hopefully find those values here, and our model should run. So let's give this a shot. So I'm going to go ahead and hit play, and look at that, it ran. So if I come here to my scope, and yep, this looks totally reasonable. And now we see the power of defining these variables here in a script. If I want to change something, like I want to increase the damping, like how about here, I just need to come back to my model, change that number, run it again, and come back to my Simulink model, hit play, and I should have some new results with a new damping. And yep, look at that. The system seems to damp out a lot quicker here. So this is a very powerful technique, and you know what? You can change more than just simple gains and things like that. So for example, in the simulation parameters button, we can do all sorts of fun things here. So for example, instead of stopping at 30 seconds, we could go ahead and say, how about T final? And, you know, and if we come back to our scope here, we noticed this was fairly jagged here. If we wanted to smooth this out, we could try to tell Simulink, you know what, don't take such a big step here. If I come here to my simulation parameters, again, I come here to additional options. In the max step size, maybe I'll call this, how about T step max, right? Hit apply, hit OK. And again, all I need to start doing is define more parameters here. So I think we had something like called T final. Let's maybe make this, how about 45 seconds here? And how about T step max? We'll say don't take anything bigger than a 0.05 second step. So now again, if I run this script, all those should be initialized. So if I come here to my Simulink model, hit save and hit run, we should have this change. So if I open up the scope, you'll look, everything looks a little bit smoother. Simulink is taking smaller time steps, and it's running all the way out to 45 seconds. We can also do things like change the initial condition. So why don't we come in here to the integrator? So in this integrator, if I double click on the integrator block, instead of having an initial condition of 0, let's just how about put theta 0. And similarly for this integrator, instead of 0 for theta dot, we'll say this is theta dot 0. Hit OK, save, and finally we just need to come back to our script here and start defining these variables. So maybe let's have the pendulum start at, how about negative 30 degrees, negative 30 times pi over 180, and how about theta dot 0, sure, we can leave this at 0 for now. Okay, run this script again, and come back to our Simulink model, hit run, and again, here we are, starting at negative 30, and things are going well until the step function comes in at 10 seconds and pushes the block a little bit further. So this is a great way to define model parameters here. So you have a Simulink model. What you should be doing is using variables everywhere for block parameters, for simulation parameters, for initial conditions. And then before you run the Simulink model, you should just have a Matlab script whose sole job in life it is to initialize all of these variables so that they appear in the workspace before you start the simulation. Now, the one problem with this workflow is that we had to run the Matlab script, go over and open up the Simulink model, press play on the button here, and then take a look at the scope here in order to see any results. Now, in this day and age of automating everything, wouldn't it be great if we could execute the Simulink model directly from the Matlab script? Well, the answer to that is yes, it would be great, and luckily there's a command to do that. So what we can do here is if we go ahead and use the sim command and we pass it the name of the model, so let's go grab the name of the model here. I think, we called it PendulumModel.slx. Pass it to that as a string here. What this is going to do is this line will execute and run the model here. So to illustrate this, why don't we go ahead and, you know what, let's change the initial conditions. Maybe let's go back to 0 everything here, and maybe let's go ahead and undock this here, so that we can see both the script on one side, and then maybe let's put the scope here over here. Now let's go ahead and I'll put a breakpoint like such. Let's go ahead and run this, and now we're sitting here waiting on line 20. So when line 20 is executed, the sim command, what that's going to do is basically the equivalent of us going over, opening the model, pressing the play button here. So let's go ahead and continue here, and hopefully to keep an eye on that scope here. And there you go, right? You see that it was executed and the simulation was run. In fact, the Simulink model doesn't even have to be open. Let's go ahead and close the entire Simulink model here. And I'll take away the breakpoint, and you can run this again here. And it will execute the model. Of course, we're sort of taking that for granted right now because the Simulink model is not really sending data back to Matlab at this point, so there's nothing for us to really see being generated by the Simulink model. So why don't we go ahead and fix that now? Alright, so to fix this, let's first go ahead and redock the editor here into Matlab here, and let's go ahead and reopen that Simulink model here. So maybe I'll just come here to current folder, and I should be able to just double click on the Simulink model to open it. Now, what we would like to have happen here is I would like it that when this Simulink model runs, I would like to send some of these signals back to Matlab here. The easiest way to do this, well, actually no, I take that back. One way to do that here is let's just come ahead and open up our library browser, come here to Sinks here, and let's look at using this block here. It's called an out1 here. It's just called out1 because this happens to be the first output. So if I, for example, want to send theta back to the model, let's just go, or back to the Matlab workspace, let's just branch off the theta, connect it like such, and save the model here. Now, tell you what, let's close some of this stuff here. And actually, you know what? We can close the entire Simulink model if we'd like. Close the Simulink library browser. Let's again come back to the workspace. I'll maybe make this a little bit bigger here. Take a look at all of the variables that are created here right now. Now, what I'm going to do here is let's run this one more time, and we're going to see one more variable that's going to be created. It's called out. And that is what's being generated by that little out1 block that we created and added to our model. So again, if I run this, it will run the script, and when we hit line 20, it will execute the Simulink model, and hopefully the Simulink model will send data back here to the Matlab workspace in the form of that out variable. So let's go ahead and hit this button right now to run the script. And there it is. This thing called out was created by Simulink. So let's take a look at what this is. And we'll see that out, it's actually a somewhat complicated data structure here. So what we need to do is actually just extract data, unpackage this data here. So let's go ahead and maybe, I guess I probably should have commented it here. What we were doing here is run the Simulink model using the sim command. And now that we've run this, we want to extract the data generated by the Simulink model. Right, so it was sent back to the workspace, so all we have to do is extract that here. So the syntax for this is a little bit esoteric here. You'll notice here, let's go back and take a look here at the Simulink model here. Maybe I can close this. You'll notice that this Y out signal was hooked up to the theta signal, and the signal was named theta here. So when we come back here, we notice that, you know what, there's one element and it's called theta. So in order to do this, what we do here is we're going to first go ahead and extract the signal itself. Maybe let's call this theta signal. And what I'm going to do is I'm going to say yout dot get element. And what element do I want? I want the theta element here. Okay? And then once I have that, I can extract the time by just saying something like theta signal dot values dot time. And now what I can do is I can get out the actual theta value that corresponds or line up with those timestamps t. So I'm going to say theta is theta signal dot values dot data. Okay, and I'll put a semicolon here, and let's go ahead and run this. And again, I should come back here to the workspace, and now we see we have theta and time. They're 903 elements long here. And what I can maybe do now is, why don't we plot those to see what's going on? So if I say figure plot t theta, x label should be t in seconds, and the y label, the y-axis should be theta in radians. Maybe we'll turn the grid on to make this thing look pretty, and maybe as a title we'll say data generated by the Simulink model. Right, let's save this, and now if I run this, this is actually very exciting because look at that. We are now getting data back from the Simulink model, right? This trace was generated by Simulink, but now it's here in Matlab, right? We can now use this to do analysis or other interesting data processing. So for example, you know, what if we wanted to find the maximum value of this signal here? Back in Simulink, that was very hard to do here, right? Because that would involve you just eyeballing it off of a scope. But now that we have the data in Matlab, we could actually go ahead and do that. So for example, if I want to find the peak here, let's go ahead and do that now. Now that I've got the signals, I could do something like just saying, you know, theta max and the index at where this happens. I'm just going to use the max function here. I'm going to look for max of theta here. And then I'll maybe, the time that this occurred here is time at the index max. And now what I can do here is, let's come here and I'll turn hold on. So I'll plot both the signal and I'll go ahead and plot the time when the theta max occurs. Let's again plot this as a red X. Marker size 14. Again, if these are not familiar to you, all these plotting commands were covered in our 2D Matlab, or our 2D plotting with Matlab tutorial, so I'll leave a link to that in the description, and you should also have a link on your screen right now to watch that if you're interested. But again, let's, oh, you know what, one more thing, let's add a legend here, how about? So how about, let's say the first one is theta, and then the next one is the maximum value of theta. So now, this should be, aha, look at this. This is really, really exciting, right? We're able to now identify maximum, minimums. We can do all sorts of other sort of analysis as well. All right, so let's come back to the Simulink model, and we saw that the way we achieved this here was using this out1 block. I would like to show you a little bit more syntax while we're at this, because in a lot of cases, you may want to log more than one signal, or you may want to log actually vector-based signals. So what I mean by that here is, tell you what, let's delete this signal right here. And let's go ahead and grab a mux here. So I'll come here and open my Simulink library browser here, and I'll get my signal routing and find a mux block. Drag this in, and again, a mux here should be able to concatenate multiple signals together. So what I want to do here is I want theta as the first input to this, and maybe how about theta dot? So I want the position and the velocity of the block here. So now let me hook this up here, and now this, oops, let me line this up here. What we're now logging is a vector maybe more aptly called, let's call it X for the entire state vector of my system. theta and theta dot here. And one thing that might be helpful to realize that this is now a vector here is let's go ahead and turn on the display here to show the signal dimensions. So I'll come here to display signals and ports, and I'll click on signal dimensions, and we see a 2 show up. So we see right now what we're actually logging here or sending back to the Matlab workspace is a 2-element vector here, right? It's theta and theta dot here. So if I do that and come back to my Matlab script, I see I'm going to have to make one small change. The small change in syntax now is that data is actually going to be a matrix. It's not going to be a vector any longer. In fact, it's going to have 2 columns here. The first column is going to be the first element of that vector. The second column is going to be the second element of the vector. So I just need to modify this to say, okay, theta is actually the data here, but it's all rows column 1 here. And now theta dot is this same thing. Let me maybe get the white space a little bit cleaner. Right? Except it's all rows column 2. Okay? So now what we can do here is, again, let's go ahead and convince ourselves of that. Maybe what we should do here is, let's start a subplot maybe, 2 by 1 by 1 here, and maybe the next one here, 2 by 1 by 2. Let's go ahead and plot t and theta dot here. And again, we can go ahead and pretty up the plot if we like. So x label is again t, but now the y label is actually, it's d theta dt, right? It's theta dot in terms of rad per second. So now if we run this, whoops. Oh, sorry, yep, I need to modify this. So if you remember right, we changed the out one block to be hooked up to not the theta signal anymore, but to a signal that we labeled x, right? So if you come back here and look at the model here, right, this is now hooked up to the signal called x, which was our vector here. So let's go ahead and change that here to get the x signal. So if we run this again, aha, here we are. Now this is all working. So now we've got the position here as well as the velocity as well, successfully being exported from the model. So that's great. So that shows how to use the out1 block to save either a scalar or a vector signal from Simulink and send it back to Matlab. Let's look at a second technique to do a very similar operation here. All right, so let's go ahead and again open up the library browser here. And if we come here to Sinks here, you'll see there's a block here called To Workspace. Let's grab and drag and drop that into our Simulink model here. And what we're going to see here is I can go ahead and double click on the block, and let's change the variable name to maybe be called something like SimX here. And while we've got the parameters open, let's go ahead and take a look down here in the save format. Notice that the default one is time series. If you click on this, you'll notice there's actually multiple different ways you can save this, but let's start with just the default time series. So again, let's go ahead and just hit OK. We've now got this To Workspace block. Let's just go ahead and hook up the signal X to that, save our model, and now come back to Matlab. And when we go ahead and run this, and excuse me, I should come back here to the workspace here. We notice here now that there's this variable called SimX here. And we see that again, SimX is similar to the yout signal in the sense that it is a complicated data structure here. So all we need to do here is just unpack that data to get at the signals that we want. So let's go ahead and maybe put in a couple of notes here. Oh, and actually, gosh, I just noticed here, maybe I want to change this code. I want to make sure this is all appropriate. You remember this was our previous version here where we were unpacking the data from yout. I better call this now, let's call this X signal, right? And I'll hit Shift Enter to replace all the instances of that just to make everything consistent here. Okay, now I know, again, that was just a little bit of me being a little anal retentive to make sure the code is clean here, because what we're trying to do right now is actually, I don't want to be using the yout data here, so I'm actually going to comment this entire block out. Instead, what I want to do is I want to get theta and theta dot from this SimX variable that we obtained using the To Workspace block. So maybe what I'll do is I'll write a little note here and I'll say extract the data generated by the To Workspace block. And what we can do here is we can contrast that here with extract data generated by the out1 block is maybe a better description of that comment block above, okay? So in order to do this, all we got to do here is go ahead and extract the data here. So the syntax, again, it takes a little while to just figure it out, but it's not that bad here. So I'm just going to say T is simX dot time, and theta here is going to be simX dot signals, or sorry, excuse me, dot data, all rows column 1 here, and theta dot is going to be simX dot data, all rows column 2. Again, because we saw that X was a vector, right? It's a 2x1 vector. And let's just go get the white space all lined up here so we can see everything cleanly. Great, so now if we run this, we see that we get the exact same results, right? The data is now being sent back to the Matlab workspace using this To Workspace block. Okay, so before we leave the To Workspace block, maybe what we should do here is let's come back to the model, and I just want to show you here that, you know, there's multiple ways that you can save the data. We saw here that earlier it was with the time series. There's other options. The one I actually used like quite a bit is this structure with time. I use this in a lot of my models just because I'm a little bit more familiar with it here. So if you change the save format to, say, structure with time, all we're going to have to do here is just change the way that that SimOut variable we extract the data from that SimOut variable. So what I mean is if we run this, this is obviously not going to work because the data structure of SimOut has changed here. So if you take a gander at this thing, you see it's just got a little bit of different formatting here. So all we got to do is extract that. So what we should maybe do is let's first expand this comment here. So this code right here is how to extract data generated by the To Workspace block using a time series, right, structure. And now what we want to do here is let's get code here that is going to do this exact same thing where we're going to extract data from the To Workspace block, but instead this is now using a structure with time format, right? So in this case, all you do here is the time is now simX dot time here. Sorry, excuse me, lowercase time. And then theta is going to be simX.signals.values, all rows column 1 here. And theta dot is going to be simX.signals.values, all rows column 2. Okay, and again, let's line up the white space so that all of our code looks nice and clean. And we see here, this is just a slightly different save format. So I'll go ahead and let's comment out the previous block here because we don't want that to execute. I want this one to execute now. So if I run this, again, we see we're back to the exact same spot here where we've got the data being sent back to the Matlab workspace now from the To Workspace block, but using two different structures, right? You can either use the structure with time format or you can use the default time series. Why don't we go ahead and switch this back to the default just because that's probably what most people are going to be using with their models now. It's going to be this default time series. So I'll go ahead and hit save, save, and then again, comment out this block and uncomment this and run again. And again, we're back to where we were. Okay. Finally, let's look at one more way that we can go about sending data back from the Simulink model to the Matlab workspace. The third and final method I'd like to talk about today here is called signal logging. So to do that, let's come back to our Simulink model here. And to log a signal, what you want to do here, it's actually sort of a multi-step process. What I would first recommend you do is take the signal that you want to log and make sure that you've named it. So in this case, we have named it. You see, we've given it a name X. That's perfect. Now, once we have a name, what we can do is right-click on the signal. Sorry, try that again. Right-click on the signal, come down to Properties, and select here. You see where it says Logging and Accessibility? Just click it and put the check mark here on Log Signal. Now, the reason that we wanted to make sure we named the signal first here is because you see here, when you're logging the signal, the default option is to use the name of the signal when logging the data back to the Matlab workspace. Of course, you could use a custom name if you want here, but I think that gets a little bit confusing very quickly here. So I would like to keep the name the same as what I've named it in the Simulink model, so I'll go ahead and keep this as a default. I'll go ahead and hit Apply and hit OK. And notice here that you get this little icon. It looks like this little wireless streaming icon here on the signal. That's Simulink telling you that that signal is being logged or saved here. The other place that you can tell that that's happening here is now that I've enabled this signal to be logged, let's come up here to my model configuration parameters. And when I come to the data import export side right here, you'll see down here in signal logging here, this now has a check mark, and you see what it's going to do is it's going to create a variable called logs out in the Matlab workspace here. And if you go ahead and move a little bit further to the right, and you say configure signals to log, if you click on this, what we should see now is, check it out. Here it is. Here's that signal X that we set up earlier, and it's now set up to be logged and sent back to the Matlab workspace. So great, let's go ahead and close this. And we can close this as well here. Oh, maybe one more thing while we've got this thing open here. You might have remembered earlier when we were using the out1 block and it was creating this variable called yout. Well, here you see exactly where it came up with that name here, right? And we also saw that here's thattout that's automatically being created when you run the model here. So in this data import export pane of the model configuration parameters, there's a lot of stuff you can configure here to get data back from the Simulink model back to the Matlab workspace. But again, let's leave everything default here for this tutorial. So I'll go ahead and cancel this because we actually didn't change anything. We just looked at things here. And now if we go ahead and save and run the model here, and we come back to the workspace, we see here that we've got this variable called logs out, which again is a complicated data structure here that we just need to extract the data from. So let's go ahead and do that right now. So again, let's comment this section out. We're not using the data from the To Workspace block anymore. I want to use the data from the logs out object. And what's actually really nice about that is the save format is very similar to using that out1 block. So I can just go ahead and copy this entire block of code. Let's come down here and say, I want to now extract the data generated by the signal logging technique. All right, so I'll paste that here. Let's go ahead and uncomment this section here. All I got to do is basically change the name of this. Instead of using yout, I'm going to use logs out. Okay, so if I run this, we should basically be here again. There's the third way to skin this cat, right? Is you can now use the logs out method here. All right, so that was covering how to get Matlab from the Simulink model into the Matlab workspace. What if we want to go the other direction? Namely, what if we have data that we've loaded into the Matlab workspace and we would like to use that to drive the simulation or be part of the input of the model? So in order to do that, let's come back to our Simulink model and again, open up our Simulink library browser, and instead of sinks, let's come here to sources. And if you scroll through this, you'll see that there's a block here called From Workspace. If we grab and drag and drop this into our model, what we're able to do here is we can double click on the block, and what we're going to do is create a variable in the Matlab workspace called, in this case, how about SimT, for this is the torque. So again, I apologize for the nomenclature. Lowercase t is going to be time, uppercase t is going to be the input torque to this system, right? So if I hit OK here, what I would like to be able to do is, let's make this model a little bit bigger so we can get a little bit more real estate here, is instead of using this boring step function, what if we had this coming from the Matlab workspace, the torque was something more interesting, like say a ramp followed by a sine wave. So you obviously could cobble that together with a whole bunch of Simulink blocks, but it would be really nice if we could load that in from the Matlab workspace. So in order to do that, let's first go ahead and maybe let's just put a switch here first so we can choose which one we would like to use. So I'll grab a manual switch block here and let's just disconnect this. So hopefully this will make a little bit more sense once we get everything connected up here. Okay, and then I'll connect this block like such. Oops, sorry, click here, click there. There we go. So now I can either use the boring step function, or if I turn the manual switch down here, I can use the input coming from the Matlab workspace as the input torque to this system, okay? So let's go ahead and save the model, and let's come over to the Matlab workspace here and create this variable called SimT. All right, so I'll come over here, and maybe let's scroll up to the top here, and before I run the model here, let's just go ahead and start a new section here and call this create an input called SimT, which will be used as input to the Simulink model. Okay, so let's go ahead and do that now. So in order to do this, I need to make this variable called SimT that has a very particular structure. And that structure is, it just needs to be a matrix with two columns. The first column needs to be the time stamps, and the second column needs to be the associated value of the signal at that given timestamp. So let's go ahead and do this now. So I'll maybe make a variable called T, and this will be the time. So let's make this linspace, maybe go from 0 to T final, and maybe let's use 30 steps here. And the one slight nuance is we're going to need a transpose here, because linspace is going to give me a row vector here, and I actually want a column vector here. So tin is just a column of all of the timestamps, and now all I need to do is create another variable. Maybe let's call it capital Tin for the actual torque at each one of those times here. So let's go ahead and first make this just a whole bunch of zeros, the same size as Tin. And what I want to do is now I want to fill in all of this with whatever custom values I want. So you might be able to load this in from a data file, but in this case, to keep everything self-contained, why don't we just procedurally generate what this should look like? So let's just do something like, how about for k gets 1 to length of Tin. Let's go ahead and make this, again, we'll make it a ramp for the first 10 seconds, and then after that, we'll maybe switch it over to a sine wave. So we could do something like, if Tin sub k is less than 10, then the actual value of the signal, or the input torque here, is just going to be the time here, right? So it's just going to be a ramp with slope 1, right? And then else, if the time is greater than 10 seconds, let's just make it a sine wave. So how about Tin sub k is just going to be sine of Tin sub k. Something like that. So that should be pretty simple. Let's just go ahead and check this input for completeness. So maybe let's just say figure plot Tin versus Tin here. And we'll just go ahead and put a breakpoint here. We won't run the whole thing. I just want to double check to make sure we created that signal properly. And yeah, here we go. So for the first 10 seconds, it's a ramp, and then we go into this very coarse sinusoidal input. I guess maybe this is a little bit too coarse for our liking. Maybe we should increase this. Instead of 30 steps, let's make this, how about 100? Let's quit debugging, and we'll rerun again just to make sure that this seems reasonable. There we go. Okay, so here we go. We got a ramp, and then we got a sine wave input for the rest of the time. So this looks beautiful. So we've got these two signals put together. So all we need to do now is basically just say something like SimT, right? That was that variable that we created. Again, it just needs to be two columns here. The first column is the times. The second column is the associated signals there. So now we've got, you see this block of code here is just generating the input signal that if we come back to the Simulink model, will be fed in via the from workspace block, and that will be used to drive the entire simulation. So again, let's take out the breakpoint here and just run this, and let's see. We should now be seeing, here we are. Here's the response theta of the pendulum to that input, and we see, yeah, it looks like it's ramping up, and then it goes into this interesting behavior as due to the sine wave. So this looks awesome. I think we've got most of the inputs here, or we've got most of the necessary tools to get data from Simulink and also sent to Simulink. So this is looking great. All right, so maybe the last thing I'd like to show you that might be helpful when you're interacting with the Simulink model via Matlab Script is the open command. Tell you what, why don't we put this in right before we actually execute the simulation via the sim command? So it might be helpful sometimes to simply open the Simulink model so you can see what you're about to simulate. So in order to do that, it's actually really simple. It's just call open, and then you pass it the name of the model. So we've got the name of the model down here. So if I pass this in here, what line 36 is going to do is going to open the model before we actually run the simulation here. Again, this is completely optional. Maybe we should put a little note here. This is completely optional. We saw that the sim command has absolutely no problem running the Simulink model if it's closed here. This is purely for aesthetic purposes, just so you can see the model that you're about to run. So let's go ahead and run this again. And here we are. Everything is working. I think we've done everything we'd like to achieve or accomplish here. So let's just take a real quick recap. I think what might be helpful is let's just walk down this script that we've gone ahead and generated, because like we said, the point of this video was to show how you could interact with the Simulink model and control it via a Matlab script here. So Obviously, our first block here, this is our normal clear CLC close all here. This is where it starts getting interesting, right? The very first thing that we usually do, that I always recommend in terms of a pattern here when you're interacting with the Simulink model, is the first thing you do after you do your clear CLC close all is define some of the model constants. Any of these parameters like gravity, mass, damping ratio, length, any parts of the model here, they should just be defined, as well as any simulation parameters, things like the simulation time, the time step, initial conditions. All of these are needed to generate, to be defined in order to get the model to run. Similarly, what we next did is we created some data that could be used using the from workspace block here. So again, this could be something where you would load it in from a data file here, or you procedurally generate the complicated signal that you want as an input right here. Whatever you like to do. So at the end of line 33, we have defined pretty much every single input that the Simulink model is going to need to run. Then what we do here on line 36 is we use open to just simply, again, just open the Simulink model. It's just saving us the work of going file, open, and browsing to the model here. This is completely optional and is purely for aesthetic purposes. The real magic happens here on line 39 when we are going to use the sim command and pass it the name of the Simulink model we want to run. What that's going to do again is it's just going to go ahead and press the play button in that Simulink model and have it generate the necessary data for our analysis here. After we run the model here, right, we saw that if we had properly instrumented the model, namely with either out blocks, To Workspace blocks, or logged appropriate signals, that would then get sent back to the Matlab workspace here. So again, line 39 is doing an incredible amount of work, right? All of the heavy lifting is done with line 39, right? But it's the Simulink model that's doing all the heavy lifting here in terms of generating the data here and running the simulation. After we do that, the next thing you're going to have to do is you're going to have to extract all that data that was created. So let me just uncomment all of these blocks of code so we can see what's going on here. So again, we looked at multiple different ways to extract data. So we looked at using an out1 block here, right? And if you wanted to use an out1 block to get data, here was the appropriate syntax to extract the relevant data from that block. Again, this is not my favorite method. I actually really like the To Workspace block here. So we saw that there were multiple ways that you could use a To Workspace block. You can either use a default data structure of a time series, and if you wanted to do that here, here's the syntax to go about extracting that data. Or you can use this structure with time format. All you have to do is just change the syntax of how you're going to unwrap that data structure that was passed back to you. And finally, we looked at sort of the newest way of going about doing this is logging the data, using signal logging to log that data to this logs out variable. And again, if you wanted to do that, here was the syntax in order to do that. Now, once you were able to do that, maybe we should put a few more comments here. After that, you're free to do analysis using Matlab on the data here, right? So again, you can use all of Matlab, min, max, FFT, any functions you want. You can call it on the data, you can analyze the data, you can do whatever you like here. For in this case, we're finding a max, and then we're just visualizing it here, right? So there you have it. This, I think, is our entire workflow here for using Matlab to control the Simulink model and to interact with it. So let's just jump over to a quick set of summary slides so we can recap what we talked about today. All right, so to summarize what we covered today, we started out talking about how you can define variables in the Matlab workspace, which are then going to be used by a Simulink model here. This allows you to generate a much more robust and dynamic Simulink model that's able to adapt to changing parameters. We then looked at the sim command, which allowed us to basically run a Simulink model from a Matlab script. After running the model here, one of the things you probably want to do is you want to send that data back to the Matlab workspace. So we looked at 3 different ways to do that. First, using the out1 block, which we saw is actually not a very good way to do it here, and it's more presented here out of academic interest than anything else. The more popular and actually my preferred way to do this is to use the To Workspace block. And finally, we looked at also how to log the signal if that's how you would like to get data back to the Matlab workspace. Lastly, we then looked at sort of the opposite direction operation in the sense that now what if you had MATLAB data defined in your workspace that you want to use as input to a Simulink model? We looked at how to do that using the From Workspace block. So, I hope you enjoyed the video and it was useful for your interactions with MATLAB and Simulink. If you did like it, please subscribe to the channel here. You can do that by clicking on the icon that should have just showed up on your screen. We will be having weekly videos on MATLAB and other engineering software tools and other topics of interest as well. So, with that being said, I hope to catch you at a future video. I'll talk to you later. Thanks. Bye.